Hello everyone. Today we will start by learning about absolute and local minimum and maximum. So we will start with the definition. Let C be a number in the domain D of a function f. Then f of C is the absolute maximum value of f on D if f of C is greater than or equal to f of x for all x in D. Now f of C is the absolute minimum value of f on D if f of C is less than or equal to f of x for all x in D. So let us look at this graph in order to clarify the definition. At the point x equals to 3 and f of x equals to 5, this point is the highest point in the graph. This is what the definition refers to as f of C being greater than or equal to f of x for all x in this graph, for all x in the domain. Because of that, we call this point the absolute maximum, and another word for absolute is global. Now we also have what we call the absolute minimum, which is at x equals to 6 and f of x equals to 2. So this is the lowest f of C in the graph. So this is what we call the absolute minimum, and this is what the definition refers to as f of C being less than or equal to f of x for all x in the domain of this function. Now, when we're looking at this graph for the absolute minimum or absolute maximum, we looked at either the lowest or the highest point on the entire domain of this function. However, if we limit ourselves to a smaller interval or a smaller part of the function and find the minimum or maximum on this smaller part, this is what we call the local minimum or the local maximum. So let's look at the definition. The number f of C is a local maximum value of f if f of C is greater than or equal to f of x when x is near C. It is the local minimum value of f if f of C is less than or equal to f of x when x is near C. So let's look at this graph. We will start by identifying the absolute minimum and the absolute maximum, and then we will choose some intervals in order to identify either the local minimum or the local maximum. So first, let's start with the absolute minimum. So the lowest point on the graph is at x equals to a, so this is what we call the absolute minimum. And the highest point on the graph is when x equals to d, so this is the absolute maximum. Now we will choose some intervals. Let's start with the interval a till c. I will highlight it in green. So we will identify the local minimum or the local maximum. What is the highest point in this interval? It's when x equals to b. So this is the local maximum. And now we will choose another interval, perhaps from maybe b till d. So I highlighted it now. I will write with a different color from b up to d. So let's identify the local minimum in this interval. So what is the lowest point in this interval? It's when x equals to c. So this is our local. Now there are just a few things I would like to point out. So this is the graph of x cubed. One thing you might notice, the graph on top will keep on increasing, and at the bottom it will keep on decreasing. So we don't actually have an absolute minimum or an absolute maximum. So no absolute minimum or maximum for this graph. Now let's look at a few other graphs. So the graph in figure 9, all of these figures come from the book, and these two come from page 282. So let's look at figure 9. So let's try to find the lowest point on this graph. It is when x equals to 2. So x equals to 2 is the absolute minimum. And let's try to find the highest point on the graph. You might say that it is when x equals to 1. However, this point right here is not defined. It's not part of the domain because we have an empty dot right there. So in fact, we don't have a maximum value in this graph. Now let's look at figure 10. So we have an asymptote at x equals to 2. So the function will keep on increasing but never touches x equals to 2. Therefore, we don't have a maximum. Now regarding the minimum, again, this point at x equals to 0 and f of x equals to 1, or I mean g of x equals to 1. So this point right here, we have an empty dot, so it is not part of the domain, so we do not have a minimum. Now let's look at what we call the extreme value theorem. So if f is continuous on a closed interval a till b, then f attains an absolute maximum value f of c and an absolute minimum value f of d at some numbers c and d in the closed interval a till b. So let's look at these graphs. So let's notice that f is continuous in all of these graphs from the interval from the closed interval a till b. We can notice that f is continuous. So the extreme value theorem tells us that f will have an absolute maximum value and an absolute minimum value. So let's see in the graphs, they labeled the maximum value as c, so this is f of c, and we can notice that this is the maximum. And now in the second graph, this is f of c and it's the maximum. And in the third graph, we have f of c1 and f of c2, both are equal and both of them are maximums. So the next thing the extreme value theorem tells us is that there's also a minimum value f of d at some number, d between a and b. So here's our d, this is our absolute minimum. And in the second graph, d happened to be equal to b. And in our last graph, this is our d, it's the absolute minimum. Now let's move on to learn about Fermat's theorem. So if f has a local maximum or minimum at c, and if the derivative f prime of c exists, then f prime of c is equal to 0. So let's look at what this means by looking at this graph. So at point C, we have a local maximum. It might be the absolute maximum, but we are not sure how the graph continues beyond what we see right here. And at point D, we have a local minimum. So what Fermat's theorem is telling us that if we draw the tangent line at a local maximum or a local minimum, so if we draw the tangent line at either C or D in our cases here, we notice that this tangent is horizontal. So its slope is 0. So this is what Fermat's theorem is telling us. So if we have a local maximum or a local minimum, then the slope of the tangent line is 0. And another way to refer to the slope of the tangent line is the derivative at a point. So the derivative at a local maximum or a local minimum would be 0. However, one thing to point out is that the converse of this theorem is not true. So this theorem does not mean that if we have a minimum, this theorem does not mean that we have a minimum or maximum every time the derivative is 0. And we will see examples where to verify this, but this just is saying that the converse of Fermat's theorem is not true. So let's look at a few examples to verify that the converse is not true. So in the graph of x cubed, again, we did look at this graph a few minutes ago, and we noticed that there is no absolute minimum or maximum. And I would like to add that there's also no local minimum or maximum. Now let's look at the graph. When x equals to 0 and y equals to 0, if we were to draw a tangent line at this point, we would get a horizontal tangent line. Horizontal tangent line means the derivative at this point, so f prime of 0 is equal to 0. However, even if we have the derivative at 0 to be 0, this does not mean that we have a local minimum or a local maximum, because looking at the graph, we do not have a local or an absolute minimum or maximum. Now let's look at absolute value of x. In fact, for absolute value of x, we do have uh, uh, an absolute minimum, or you can call it a local minimum if you were to limit and take an interval. But if we're looking at the entire domain, so we do have an absolute minimum at x equals to 0 and y equals to 0. However, at 0, 0, these are the coordinates, y is not differentiable. And we agreed about this before when we learned that if we have a corner or a curvy corner or a discontinuity or a vertical tangent line, a function would not be differentiable. So in this case, function is not differentiable, so we do not get what Fermat's theorem states. However, just let us reread Fermat's theorem to get it correctly. Fermat's theorem says that a local minimum would have a derivative equal to 0 if it exists. And for our case, it is not differentiable at this point. Now, what is a critical number? Let's look at the definition. A critical number of a function f is a number c in the domain of f such that either the derivative at point c is equal to 0 or the derivative at c does not exist. So I just wanted to link this definition to what we were doing earlier. So earlier we said that if we have a local maximum or minimum, then the derivative at the point c is 0. This means if we have a local maximum or minimum at c, then c is also a critical number. So let's take an example and see how we solve such questions. So this is example 7 from the book. We will find the critical numbers of f of x equals to x cubed minus 3x squared plus 1. This is from page 284 in the book. And we will only do part A for today. So if f of x equals to x cubed minus 3x squared plus 1, we would like to find the critical numbers. So we will start by finding the first derivative of f of x. So we do the power rule. This gives us 3x squared minus 6x. And then we solve the derivative to be equal to 0. So a good thing might be to factor out the 3x. This gives us x minus 2. So 3x times x minus 2 equals to 0. So 3x equals to 0, and therefore x equals to 0. Or x minus 2 equals to 0, so x equals to 2. So these are our two possibilities for us to have a derivative that is equal to 0. Now, please note that a critical number, again, let's read the definition, is a number c in the domain of f such that either the derivative at this point equals to 0, which is what we did right now, or the derivative does not exist. So, does 3x times x minus 2 ever not exist? It actually is a polynomial, so it exists on all reals. Now, one more thing to notice about the critical numbers is that they have to be in the domain of f. Now, let's check. What is the domain of f? F is also a polynomial, so the domain is all real numbers. So x equals to 0 and x equals to 2 are both critical numbers. Now let's learn about what we call the closed interval method. So, as the name suggests, when we have a closed interval, we have 2 points, so maybe A till B in a closed interval, so it includes both of these points A and B. What does the closed interval method help us to do? It helps us to identify maximum or minimum. So the maximum or minimum occurs either at the endpoints of the interval or when the derivative equals to 0. So let's take an example. Let's find the absolute maximum and minimum of f of x equals to x cubed minus 3x squared plus 1 over the interval -½ till 4. And this is from page 284 in the book. So one thing to start with is to note down our endpoints. So our endpoints are -½ and 4. So what we do is we find the value of the function at x equals to -½, so f of -½ and f of 4. So what is f of -½ This will give us -½ cubed minus 3 times -½ squared plus 1, which will evaluate to 1 over 8. Now what is f of 4? 4 cubed minus 3 times 4 squared plus 1, which will give us 17. Are we done? No, we are not done, because we said that a maximum or minimum can occur at the endpoints of the interval, which we did. Now we need to cover the second idea, when the derivative is equal to 0. When is the derivative equal to 0? In fact, we already worked with this same function a few minutes ago. This is the exact same function, and we said that the derivative equals to 0 when x equals to 0 or x equals to 2. So let us find f of 0 and f of 2. So what is f of 0? It's 0 cubed minus 3 times 0 squared plus 1, which is equal to 1. And what is f of 2? It's 2 cubed minus 3 times 2 squared plus 1, which gives -3. All you have to do right now is look at all of these answers that you got. Which one is the smallest one? It's the -3. This means we have an absolute minimum here. So an absolute minimum when x equals to 2 and f of x equals to -3. Now, which one of the other numbers is the biggest one? It's 17. This means we have an absolute maximum when x equals to 4 and f of x or f of 4 equals to 17. So this, what I did right here, is what we call the closed interval method. We will now move to the first derivative test. So one thing to note that when the derivative is greater than 0, the function is increasing on the interval. However, if the derivative is less than 0, then the function is decreasing on a certain interval. So let's see how this can be helpful. Given the function f of x equals to 3x to the power of 4 minus 4x cubed minus 12x squared plus 5, we would like to find when it is increasing and when it is decreasing. So first, let's start by finding the derivative. What is the derivative? We get 12x cubed minus 12x squared minus 24x. And let us factor it. So let's factor the 12x, and then all of it factors out to 12x times x minus 2 times x plus 1. Feel free to check our video about factoring for more information about how I factored this. Now, so we would like to know when the function is increasing and when it is decreasing. So we want to know when f prime of x is greater than 0 and when f prime of x is less than 0. So, in order to do this, we will start by finding when f prime of x is equal to 0. So when is it equal to 0? Let's solve for this. So 12x times x minus 2 times x plus 1 equals to 0. So 12x equals to 0, or x minus 2 equals to 0, or x plus 1 equals to 0. So x equals to 0, or x equals to 2, or x equals to -1. Now, why did I do this? Because through this, I can now draw a table, a sign table. So in the sign table, I write down all the terms in the derivative, f prime of x. So I have 12x, I have x minus 2, I have x plus 1, and then the overall derivative. I will add an extra column, and I'll show you what I will put in it. So up here, I'll start with negative infinity, then -1, then 0, then 2, then positive infinity. And I will draw the lines in order to get my sign table. So 12x, it is equal to 0 when x equals to 0. For any value above that, it's positive. For any value below that, it is negative. Now x minus 2 is equal to 0 when x equals to 2. For any value above that, it's positive, or else it's negative. X plus 1 is 0 at -1. Up here it's positive, and down here it's negative. Now let's look at the sign, the overall sign of f prime of x. In the first column, negative times negative times negative is negative. Here we get positive, and here we get negative, and here we get positive. Why did I do that? Because when f prime of x is negative, then the function is decreasing, and I will draw this decreasing arrow. When it's positive, the function is increasing. Here it's negative, so decreasing, and here it's positive, so increasing. So this is how I found when the function is increasing or decreasing. If you want, I can always write a conclusion at negative infinity till -1, union 0 till 2, the function, or I can just write f, is decreasing. And from -1 till 0, union 2 till infinity, f is increasing. Now let's look at what the first derivative test is. So, suppose that c is a critical number of a continuous function f. If f prime changes from positive to negative at c, then f has a local maximum at c. So, if f prime changes from negative to positive at c, then f has a local minimum at c. If f prime is positive to the left and right of c, or negative to the left and right of c, then f has no local maximum or minimum at c. Let's look at these graphs. So in the first graph, f prime of x is first positive and then it becomes negative. So we have a local maximum at c. Second graph, f prime of x is negative, becomes positive. We have a local minimum at c. In these last two graphs, f prime of x is positive before and after c, so we don't have any local minimums or maximums at c. Same for the last graph, f prime of x is negative before and after c, so no local minimum or maximum at c. Now let's apply what we just learned to the example we were just doing a minute ago. So right here, we can see that f prime of x is first negative, so it's decreasing, and then it becomes positive, so it becomes increasing. So let's look back down here. When it's negative and then becomes positive, this is a sign that we have a local minimum. So we have a local minimum at x equals to 1. And now right here, it's increasing and then starts decreasing. Let's look below when it's increasing and then starts decreasing, just as we have right here. And we have a local maximum at the point. So this means that we have a local maximum when x is 0. And now again, we are decreasing and then start increasing, which shows that we have a local minimum when x equals to 2. And this is how we apply the first derivative test. Now let us look at the second derivative test. So there are several things we will look at and then the second derivative test. So let's look at concavity test. If the second derivative of x is greater than 0 on an interval I, then the graph of f is concave upwards. Concave upwards means like this. If, however, the second derivative is less than 0 on an interval I, then the graph of f is concave downwards. So like this. So definition, a point P on a curve y equals to f of x is called an inflection point if f is continuous there and the curve changes from concave upward to concave downward or from concave downward to concave upward at P. So if the graph starts out like this and then becomes concave downward, so it starts out as concave upward and becomes concave downward, and here we have a point P, then point P is an inflection point. Again, we will apply all of these definitions in an example in a few minutes. Now, what does the second derivative test tell us? It tells us that suppose f prime prime, so the second derivative is continuous near C, if the first derivative, so if f prime of c equals to 0 and the second derivative is greater than 0, then f has a local minimum at c. If the first derivative is 0 and the second derivative is less than 0, then f has a local maximum at c. Just to remind you that whenever we had the first derivative to be 0 from Fermat's theorem, this was an indication that we possibly have a local minimum or maximum at that point. So when we find that using the first derivative, then we look at the second derivative. If it's greater than 0, then it is the local minimum, local maximum. And just to point out that if the second derivative of c is equal to 0, then we don't have any, like the test is inconclusive. We can't reach a result using the second derivative test. So now let us look at an example. So suppose f of x equals to x to the power of 4 minus 4x to the power of 3. This is from page 302 in the book. What we would like to do is to find the concavity, the inflection points, any critical points. We would like to find the local minimum or maximum. So we will begin. So first of all, let's point out that f of x is a polynomial. So the domain is all real numbers. Let's now proceed to find the first derivative. It's equal to 4x cubed minus 12x squared. Let us factor it. We factor out the 4x squared. This leaves us with x minus 3. So since we're finding derivatives, we might as well find the second derivative now. This would give us 12x squared minus 24x. Let's factor the 12x, and we are left with x minus 2. So let us start with the critical points. So when do we have a critical point? It's when the first derivative is 0, and these points are part of the domain. So let's set the first derivative to be equal to 0. So 4x squared times x minus 3 equals to 0. 4x squared equals to 0, or x minus 3 equals to 0. So x equals to 0 or x equals to 3. And both of these points are critical points. Now that we found the critical points, let us move to finding the local minimum or maximum. So to do so, we can use the second derivative test, because in the second derivative test said that if the first derivative is 0, as we just found right now using the critical points, so we can just look at the sign of the second derivative test to know if we have a local minimum or maximum. So let's look at the points x equals to 0 and x equals to 3. So let's find the second derivative computed at these points. So now we are looking for local minimum or maximums. So the second derivative at 0, we plug in 0, we get 12 times 0 times 0 minus 2, this becomes 0. Again, a reminder that when this gives 0, the second derivative test is inconclusive. Test is inconclusive. So we need to do something else to know whether we have a local minimum or maximum. Now let's look at the second derivative at point 3. So this will give us 12 times 3 times 3 minus 2. So 12 times 3 would give us 36 times 3 minus 2, which is 1. So our answer is 36, which is greater than 0. Let's look up. So if we have the second derivative greater than 0, then we have a local minimum. So at x equals to 3, we have a local minimum. Now, since the second derivative test was inconclusive regarding the point x equals to 0, we can use the first derivative point to know whether we have a local minimum maximum or just nothing at this point. So let's use the first derivative test. Our first derivative, we already computed it to be 4x squared times x minus 3. So let's put all these terms in the table. 4x squared, since we have x squared, it's always positive. X minus 3 is positive if x is greater than 3, but it's negative otherwise. So the first derivative is negative on the first interval, negative also on the second interval, and positive from 3 up to infinity. Therefore, as we can see here, it's decreasing, decreasing, and then increasing. We see here it's decreasing and decreasing. It does not flip. So at x equals to 0, we do not have a local minimum or maximum. So no local min or max at x equals to 0. So let's see what the question was asking. The question asked for local minimum or maximum. We found them. Critical points, we found them. Now we still need to look for inflection points and concavity. So let's use the second derivative and use a sign table. So we already stated that the second derivative is equal to 12x times x minus 2. Let's use a sign table. So 12x here, x minus 2, second derivative, and the last row for the concavity. So let's use the intervals negative infinity up to 0 to till infinity, and let me tell you why I use these intervals. So let's, in order to find which numbers in the intervals, we set the second derivative to be 0. So 12x times x minus 2 equals to 0. Either 12x equals to 0 or x minus 2 equals to 0. So x equals to 0 or x equals to 2. And these are the points that I used up in my sign table. So 12x, it's negative, it's 0 when x equals to 0, and then positive on these other intervals. X minus 2 is 0 when x equals to 2, positive when x is greater than 2, and negative otherwise. So the second derivative is positive, then negative here, then positive. Positive means upper concavity, negative means downward concavity, and then again we have upward here. So what does this tell us? First, to identify concavity, we can write this as intervals. So from negative infinity up to 0 union 2 till positive infinity, we have upward concavity. And from 0 till 2, we have downward concavity. Now, where does the concavity change? So here we have upward, it switches to downward. This means that at x equals to 0, we have an inflection point. Again, here we have downward concavity, it switches to upward. This means at x equals to 2, we also have an inflection point. So if we were to plug in x equals to 0 and x equals to 2 in our initial function, if we will find the coordinates, which will end up being 0, 0, and 2, negative 16. These are our inflection points. And in this way, we would have answered this question. And this question is preparing us for other questions about curve sketching.